Okay, we're recording again. Okay, so all we've done so far is identify a definition for Kc, concentrations of the products over the concentrations of the reactants, raised to the powers of their balancing numbers, and we've identified that Kc only changes when temperature changes. Apart from that, it's constant, hence equilibrium constant. What we haven't done is actually work it out. This example that I've got on the screen here is exactly the same as the one that's printed on page 11 of the topic booklet, so feel free to relax your hands and just follow along. You could always scribble some notes in on the topic booklet if that's something you needed. That's fine, it's your topic booklet after all. Okay, so let's have a look at a fairly straightforward question. 1 mole of ethanol react with 1 mole of ethanoic acid. So ethanol, ethanoic acid, we're making an ester in case you've forgotten your chemistry there, and water, that's an ester. Alcohol, acid, ester, water. At equilibrium, the amount of ester formed was 0.4 moles. So we imagine some kind of scenario where we leave the alcohol and acid bubbling away nicely in the corner of the room in some sort of system which we've set up, which is, as near as we can get to a closed system. It's constant temperature, nothing's escaping. And then we go back, an hour later, and somehow we kind of reach in and grab the ester and we measure how much we've got. I don't know how we do that at the moment, but it doesn't really matter. But that's the kind of setup. So obviously it's equilibrium, so we haven't got all of our ethanol and acid turned into ester. We've just got a bit there. And we're asked to calculate Kc from that. In fact, we need a little bit more information, but I'll come to that in a moment. So what we need to work out is how much ethanol and how much acid there is at equilibrium, which might be obvious to you now, sitting here, because it's a fairly straightforward equation. There's no balancing numbers, and if it's clear and obvious, that's great. That already means you're getting it, but I'm just going to go through it in slow motion anyway. That's kind of the problem there. We know how much ethanol and acid we start off with. We know how much ester we have at equilibrium. Presumably we started off with 0 moles of ester and water at the beginning, because you don't usually start a reaction off with product. But we don't know how much ethanol and acid we've got at equilibrium, and we need to work out the water as well. Okay, again, this might be blindingly obvious to you, but I'm going to walk us through the process. The process is called an ice table. Ice table because we look at the initial conditions and the equilibrium conditions, and then we make a note of what's changed. So I'm recommending that you draw a quick ice table under the reaction like this in the exam or on a sheet of scrap paper. And generally where students think, oh no, this is obvious, I don't need an ice table, those are the situations where people get it wrong. Okay. So if our ester has gone up by 0.4 of a mole, then that 0.4 of a mole has to have come from somewhere. So our acid and our alcohol must have gone down by 0.4 of a mole. So 0.4 of a mole of acid and alcohol has turned into 0.4 of a mole of ester and water. So we'll have 0.4 of ester, 0.4 of water, and 0.6 of acid and alcohol. Is that all fairly straightforward? Again, this isn't a particularly earth-shattering, difficult problem. The thing to note, and we'll come to this in a more complicated example in a moment, is that ignoring the pluses and minuses, if I just look at the numbers in the change row here, 0.4, 0.4, 0.4, 0.4, they're in the same ratio as the balancing numbers. So because this equation is 1 to 1 to 1 to 1, the change line is 1 to 1 to 1 to 1 as well. 0.4 to 0.4 to 0.4 to 0.4. Obviously, products go up, reactions come down. Okay, so now I know how much of these substances I have at equilibrium. I'm almost ready to plug that into Kc, but I need something else first. Kc is a measure of concentration. These are moles. So to change concentration, I need a volume. Yeah, okay. There's my Kc. So concentration of ester times water over concentration of alcohol times acid. So that's relatively straightforward, no balancing numbers. But I need a volume in there. So the concentration of, what would that be? That would be ester, 0.4 over volume. Water, 0.4 over volume. Acid, 0.6 over volume. And alcohol, 0.6 over volume. Obviously, in this case, the volumes will cancel out. In this particular example, the volumes will cancel out. It won't necessarily happen in every example. In fact, most examples it doesn't. It's happening here because we've got moles and moles on the left and moles on the right. It's a very symmetrical equation. So in this case, we don't actually need to know the volume. The volumes will cancel and we'll be left, oh sorry, it has the answer there already. 0.4 squared over 0.6 squared, which is 0.44.
Do we ever need to, will there ever be a case where we need to know the volume?
Lots. Most. Yes. Yeah. Okay. All right. Let's have a look at, if you've got your topic booklet there, we're going to all work through together the worked example on page 12. Oh. 21.3 grams of nitrogen dioxide were heated at constant temperature in a flask of volume 11.5 dm cubed. An equilibrium mixture was formed, contained 7.04 grams of oxygen. Okay, so the first thing we notice, the question is not phrased in moles at all, it's phrased in grams. That's okay. We know how to convert grams into moles, so let's do that first. So we've got 21.3 grams of NO2 and 7.04 grams of O2. Can you convert those into moles for me? Give your answer to an appropriate degree of precision. Cold tea. Not good. What have you got?
A periodic table, do you have one, sir?
Usually. Do you not have one?
Not on me now.
There you go. What have you got?
For what? The moles of KC.
NO2?
Moles of NO2 is 8.46.
Is that right? 40,
46.
46, yeah. What did I just say? I didn't? You can tell me. 7.04 gives us
4.22.
all right. Just noticed in the question it actually asks those in separate parts, but we weren't going to get very far without doing that. Okay, so let's take that information now and put it into our ICE table. So what do we know? Well, we know the initial moles of NO2 said 21.3 grams of nitrogen dioxide were heated. So that's our 0.463 right there. We assume that we start off with no products because why would you? We'll come back to the change line in a moment. The equilibrium mixture contains, what do we say, 0.22?
Yeah.
No, it's that one, isn't it? Moles of oxygen. And everything else is blank. Okay, so let's have a look at how we fill this in. Well, in terms of change, oxygen has clearly gone up from 0 to 0.22, so it's gone up by 0.22. How much has NO gone up by?
0.44.
Because
It's got twice the amount of mole.
it's got twice of the amount of moles in the equation. For every oxygen we make 2 NOs. So if I've made 0.22 oxygens, I've made 0.44 NOs, which means we can now write that in as our answer there. So that was actually the answer to question A. Now we can come back over here and identify how much NO2 has been used up. How much NO2 has been used up?
0.44.
Because?
Because it's got a balancing number of 2.
Yeah, because it's got a balancing number of 2. It's in the same ratio as NO. So if we've made 0.44 of NO, then we must have used up 0.44 of NO2. Same balancing number, same ratio. So now we can take that away, and that is 0.023. Is that right? You said that's right. Okay. So that's our ICE table fully formed there, and it's helped us get through the first couple of stages of the question. Now we write our expression for KC, so that's products, concentration of, raised to the powers of their balancing number. That's that. Products over reactants, concentrations of, raised to the power of balancing numbers. Calculate a value for the constant at temperature T and give its units. Okay, so this is going to take a bit of legwork. So now we have to use volume. The volumes won't cancel in this expression. We've got different stuff on the top and on the bottom. So we have a volume of 11.5 dm cubed. Because it's in dm cubed, I don't have to worry about any irritating conversions. So I can just go straight. Concentration is moles over volume. So moles of NO is 0.44 over 11.5 all squared. O2 is 0.22 over 11.5, and then that's all over NO2 0.023 over 11.5 all squared.
So the square brackets all can use those.
No, notice I've switched to round brackets now because we're not saying the concentration of these numbers, we're just saying these numbers. These numbers are the concentration. So round brackets, curved brackets have become appropriate again. Right. Do some button bashing. See if you come out with the same answer that I've got. Give your answer to an appropriate degree of precision. Don't worry about that. Much button bashing later. Okay. Yep. Just watch the order in which you put it into the calculator. Okay, I would do that over that equals square that. I'm tempted to write that number down.
Yeah.
You do too much on the calculator in one go. Dangerous. Your calculator makes choices that you don't want it to make. Calculations are all correct.
I think it's more.
Breaks down something. That over that equals x squared. Write that number down. Yeah, so. Oh, right. Slightly different. Okay, right, we're better.
Is there units or?
Yes, there is units. We haven't quite got to the units. You should have got an answer of pretty much bang on 7, but please give your answer to an appropriate degree of precision, which is 3 sig figs in this case, because all the data is to 3 sig figs. We haven't quite got enough time to do the units, so let's leave that for another lesson. And